Hello, Physics 30s. I want to just review with you in this video the principles of reflection and also what we call the mirror and lens equations. Reflection is actually fairly straightforward when it comes to looking at the angles. As you can see here, I'm just going to highlight the parts. I'm using Mr. Brent Klintberg's notes. They're just excellent. But if you see here, when we're looking at a surface, the reflection is where the incident angle is equal to the reflected angle. The incident angle is always measured from the ray of light to what we call the normal line, or just the normal. And that's always perpendicular to the surface, okay? But just by convention, because we have to pick one, that's how we're going to always measure angles when it comes to reflection and also refraction. We'll see that shortly. So you can see the incident angle is 42 degrees. The reflected angle is also 42 degrees. So we might say the angle of incidence equals the angle of reflection. So fairly straightforward. There's lots of examples. You know, you do a bounce pass in basketball, you shoot a puck off the boards in hockey. You can see evidence of reflection with objects, and the same thing happens with light. So I'm going to skip down here to the first application is a plane mirror. So that's just a flat mirror, like the mirrors you look at when you're, brushing your teeth in the morning. What we need to start thinking about, though, is the object that's in front of the mirror, and then the image that's produced. It looks like it's behind the mirror. In a flat mirror, as it says right here, the image will be the same size as the original object. So what you see when you're looking in a flat mirror, you look exactly as you actually are, except, reversed. But the image will also appear as far behind the mirror as the object is in front of the mirror. We call that the distance. I guess this distance here, we'd call that di, and you'll see that in the formulas. It's the distance to the image, and the distance that the object is in front of the mirror, we're going to call that do. That's the distance to the object. But don't worry about that so much. You're going to see that in the formulas later. And the law of reflection holds for a plane mirror. Just the angle of incidence is going to equal the angle of reflection. So Mr. Klintberg takes through a really quick example here. So what's kind of neat to think of is when we look at things, there is light entering our eyes. And I know we always think, when you're a kid, you're thinking of your vision. It's like you're looking out at something. Well, all you're doing is letting light come into your eye, and that light has bounced off an object and is now entering your eye, and then your brain starts processing it. It's just a fascinating process. But really, you have to think of light entering your eye in order to see something. So I'll just walk through this because you can see it in your notes. We have a nice plane mirror, and the object that we're looking at is below the eye. So when we look at the mirror, we can see the object in using dotted lines, and you'll see that's going to be the convention here for showing objects that are behind the mirror. We're going to use dotted lines behind the mirror, and the reason for that is it'll highlight this later, but that is what we call a virtual image. Virtual means it's not really there. Like if you walked around behind the mirror, there wouldn't be anything. But virtually, there is an image there. So to know where that is exactly, we could draw what's called a ray diagram. And ray diagrams just show the direction or the pathway that light could take. Obviously, there's infinite paths that light can take, but we're just going to, for these ray diagrams, you just pick the easy ones, the ones that make sense. So you can see if you're looking at the mirror, you would see the object through the mirror in that plane, but the ray of light that is entering your eye actually bounced off of, it came from this point right here on the object, went to the mirror, and then we're not going to do this a lot, but I'll mention it. See, there's the normal. So then we have the angle of incidence and the angle of reflection right there. And that light ray would bounce off the mirror and go into your eye. So Let me just clear that off so we can see the rest of this. Um, and then, of course, you could do another one from the bottom. Okay, so Mr. Klintberg did this in red. And you can see, though, that if you extrapolate the lines from your eye, so I'm going to go, like if we're going backwards, we're going this way. If you extrapolate that, eventually hit the mirror, and then you could draw that dotted line. Obviously, his looks way better than mine, to the actual image. So the ray diagram can confirm where the image should be. Now, that'll make more sense, too, as we start looking at curved mirrors. But so oh, he emphasizes the virtual image. Yes, we already did that. So we're going to look at curved mirrors now. The two obvious types are a concave converging mirror. And I will note the diploma exams have actually been fairly consistent in recent years. They've avoided using the word concave, and they just focus on the word converging. Converging is the action. This is what, think of it as, it's what the mirror does to the light. So you'll see that in the ray diagrams here in a second. It will focus the light. It'll converge the light as it hits it to a point, and then it'll spread out. Concave, if it helps, I remember it's if you look at a concave surface, it's like something you can crawl into. So it's like a cave you can get into, I guess, if that helps. But anyway, so there's just some basic anatomy that you need to understand in terms of analyzing a curved mirror. And we follow the same conventions all the time. So what we do is you take the curved surface, like this surface here, you take that surface, then we cut it right in half. It's like you bisect it. So that straight line is called the principal axis, where that principal axis intersects with the mirror. We call that the vertex. Okay, and the way that we try to sketch these, I know it's kind of hard when we're sketching them, but the curvature of the mirror, okay, whatever it happens to be, it's imagine that it just is part of a huge circle. Okay, obviously that's not a very good circle, but in fact, I could probably make that a little closer to what it really should be. Maybe something like this. Okay, so the point is that C is the center of curvature of that mirror. If you had if you could find the center. And that means then that half of that radius, okay, so from there to there is basically the radius of curvature. And then half of that, I'll just keep kind of canceling this, half of that is going to be what we call F, which is the focal length. So I'll get rid of all of that just so you can still see how that looks. But the understanding that's helpful when you're analyzing the rays that are actually going to exist when you put an object in front of the mirror. So there's actually a couple of rules, and there's quite a bit of explanation for this, but I think I can just kind of blast through it quickly for you. We're going to pretend that this arrow is an object, okay? And with that arrow sitting right there, we tend to put, just to keep things simple, we put them right on the principal axis. And then we can draw a number of rays. These are called ray diagrams. They're kind of fun to draw. So the rules for drawing these all hinge on the angle of reflection. So there's three rules, and I'll just run through them quick. So the first one is, if no matter where you put, now the issues here, you'll see we can put the object anywhere along the principal axis in front of the mirror, okay? And its position would be the distance to the object, okay? So how far away the object is from the front of the mirror. So let me clean all that up. So what we draw here is the first ray thing you can do is a ray of light could come and hit just come off of the top of the object and pass through the focal length. And so it would do, I guess I can kind of mirror this, haha, no pun intended. And what happens is that ray of light will always reflect parallel to the principal axis. And the reason for that, which I don't have to keep doing this, but it's just interesting how it all plays together. There really is a normal right there, okay? There's a normal, a perpendicular normal to the curvature of the mirror, and we can throw that normal everywhere, and the angle of incidence will equal the angle of reflection. So these rules are basically just shortcuts to explain the law of reflection, I guess, is really what it is. So anyway, you kind of get the idea of how that's made. You can draw, that's one ray that you can draw. The next one you can draw is any ray that's parallel to the principal axis. So you see that in red. It'll come and hit the mirror and then reflect through the focal length. So right here, and Mr. Klintberg did a great job of showing this, right there we have the first example of convergence. These rays of light are coming together and crossing or converging at a certain point. And we'll see why that's significant after, I mean, you can maybe start seeing it, but it'll be significant when we show one more ray here. So let's just jump to the next one. And this one is, oh, sorry, he only showed two. I thought he was going to show another one. There is one more that we can draw, and I'll just sketch it here so you can see what it would look like. Let's pick a different color here. Let's just go green. So from here, if we draw a line that hits the vertex, now I'm going to try and, yeah, pin it right there. If a ray of light hits the vertex is the point where the normal is matching the principal axis. So it's like it's a plane mirror right there, even though it's curved, but right at that point, if I can still kind of get it, I think I kind of got it. We can make that come perfect. Oh, that worked well. Okay, so the point is that that's actually another ray that you can draw. It's not necessarily a special rule, but it just confirms that everything is converging at this point, okay? So at this point right there, okay? So at that point of convergence, that will mirror the object that's above the principal axis. So right here, there actually will be light that's converging right there, and there will be an image that's produced right there. And the image will be upside down, and it'll be smaller. Okay, so you can see it's not as large as the original object, but it's smaller. We would say that's diminished. Okay, so the image would be inverted, diminished, and real. Okay, the reason we say that is because a real image, I guess I could label that. So this is real, inverted, and diminished. So we look at these properties all the time because they capture what's actually happening to the image based on where we move the object, okay? So that's great, but this is all because the object is outside of the center in this case, okay? The object is, it's outside of the center. If it was right on the center, it'll look different. And if it's right on the focal length, it'll look different. And if it's inside the focal length, it'll look different. So if you watch that video by Mr. Anderson, you'll see how that changes. But I think some of that gets addressed down here. So here's the three characteristics that I already mentioned. I already wrote them down right up here. But I guess I could connect them for you if you wish. The magnification is diminished, okay? And the attitude is basically, is it upright or is it upside down? So we identified the attitude as being inverted, and then the type. So the type, you only have two options. Either it's real or virtual. If it's a real image, I like to think of it as light is physically passing through that point. Okay, there's actual light there. And Mr. Klintberg would say if you take a sheet of paper and stick it right at that spot. So, you know, if we grabbed a sheet of paper and we put it right there, okay? If you put a sheet of paper right there, you would see the image. It would be there. It would be physically present. So that's the designation for real versus virtual, okay? So, oh, I guess he did another one. There's another rule. If you draw a ray of light through the center, so if the object is outside of the center and you were to take a ray of light and run it right through the center, it would have to hit the mirror. Sometimes the mirror isn't there, but if it does hit the mirror, then it will just bounce straight back. Okay, just like ping, ping, it goes back and forth. That would be another ray you could draw. But that's again because you're coming right through the center. So that's kind of, in that case, it would bounce just straight back. Anyway, so, let's add the last one. If you watch the video, um, when you're right at the center, what's really cool, and I'll just sketch it super fast. When you're right at the center, let's just do this. You can, what will happen is you will get convergence right underneath the object. Okay, so the image will be exactly the same size as the object, but it will be inverted, of course, and it'll still be real. But when you get on the focal point, the image is undefined. It actually doesn't exist, which is kind of cool. But if we were to put the object inside the focal length, so if we actually grabbed, here, let's change that to black. And here, I got it too big. So if we change the image, or if we move the object right there, say, okay, so we've moved it in front of the focal length, what would happen is the rays of light here would still, this one, like if we hit the mirror, it would still reflect through the focal length. So that would be one of them. Here, I guess I could make that a little cleaner. Yeah, it would still reflect through the focal length, just like that. But now, this is a little bit tight, but if there's all the other rays we can't necessarily draw because I can't have one go through the focal length. We can't touch the image and then go through the focal length because we're now in front of it. But I can draw a ray of light that comes from the top of the object to the vertex. Okay, and if that one hits the vertex, then that one will reflect at the same angle it came in at. Okay, so that would be one ray of light. Now there's no convergence though, so you can see on the the same side of the mirror, the rays of light aren't converging. But what's interesting here is if you extrapolate these lines back behind the mirror, they actually do converge. Okay, and I draw them as dotted lines because it's a virtual line. And it would create a virtual image. And in this case, what will happen now is you get a virtual object. So this is actually what a magnifying glass does. And I know you're all familiar with that. I remember playing with those as a kid. If you get the object inside the focal length, the image that you see is upright, and I should emphasize this too. This would be upright. It would be enlarged, and it would be magnified. Oh, wait, I already said that one. Sorry, not magnified. It would be virtual. Sorry, the magnification is that it's enlarged. Okay, so but it's virtual though. There's no actual object right at that point. But if you're looking at it from the other side, you see an enlarged object. So that'll hopefully make more sense if you've seen the video, but also when we start looking at some math. So you need to be able to see the different images that are produced in a converging concave mirror. Okay, now we do need to mention the diverging mirror. This is the easier one. The diverging mirror is like the bulging mirrors. Oh, you see them on buses, for example, or in convenience stores. If you walk in and there's like a big mirror like up in the corner, you look at that mirror and you can see the whole store. But what's interesting, of course, is everything you see in the mirror, it doesn't matter where you go in the store, you look up at that mirror, everything is upright, so nothing's been flipped. Like there's no point at which the image like flips and is upside down or anything. And the image is always smaller than the actual object. Okay, so in fact, I think that's what it says on, well, the on your passenger side mirrors. Okay, when you guys are driving, your passenger side mirrors, not the driver's side, that's a flat mirror. Driver's side mirrors are flat. The passenger side mirrors are a little bit convex, and they usually stencil in the mirror. It says objects in mirror are, what does it say? Are closer than they appear? I think that's what it says. Objects in mirror are closer than they appear, or something. Because you're looking at a diverging mirror, so the image gets the image is actually smaller than it really is. So anyway, but it's helpful because you can actually see a greater, have a wider range of vision with these diverging mirrors. Anyway, so um, all that's different in this case is the focal length and the center of curvature are now behind the mirror, and you still have the object in front. So he's going to start drawing the rays, and what's interesting in this case is the rays can't converge now; they diverge. So using again, it's the law of reflection. Like we can't ignore that. If you come in, if you're coming in right here, and you hit the mirror, due to the law of reflection, you're going to go that way. Okay, kind of. I guess I kind of half copied that. So there's no convergence, but what we extrapolate, I guess would be the right word, is we can draw a dotted line along along the reflected line. Okay, not the incident ray, but the reflected ray, and that will go through the focal length. Okay, now his drawing looks better, so I'll just clean that up. So now the second rule, or actually in his case, he called it rule number 3. It's a little arbitrary which ones you use. He drew a ray that would have gone through the center of curvature in this case. But obviously you can't get to the center of curvature because it's on the other side of the mirror. So his purple line comes and it hits the mirror, and then it goes right back along that plane. So there's no convergence, so there's no image that's formed in front of the mirror now. It's not even possible. But what he shows, though, is there is a virtual convergence behind the mirror, which occurs right here, right there, if you can see that. And where that convergence happens, you'll get a virtual image. But as you can tell, it is virtual, it is upright or erect, and it is diminished. So I'll post a review of both of these properties because in general, you should just know the difference between a convex and a concave, or a converging and a diverging mirror, and what the images do. But what's easy, hopefully, if you're starting to wrap your head around this, for any diverging mirror, the image is always diminished, it is always erect, and it is always virtual. Always, always, always. Okay? So that one's a little easier to work with. So the formulas. Finally, here we're going to get to the formulas. So you'll notice these on your formula sheet. They're in the middle section, I think. This is the mirror equation, and it's also the lens equation. I'll post a video on that shortly, but it works for both mirrors and lenses, which is really cool. Anyway, F is the focal length, and it doesn't matter what the units are. Usually they're in centimeters for the math that we do, but these are all distances. So 1 over the focal length is equal to 1 over the distance to the object. I won't rewrite that, but you can add that if you want. Oh, sorry, it says it right there. And then di is the distance to the image. Let me just zoom back out here. Okay, so I guess that was already there. I forgot to zoom out here. So as long as you're identifying those distances, I don't think the math is outrageous. You just have to be careful that you're doing it as the reciprocal. So you have to go 1 divided by f is equal to 1 over do plus 1 over di, and then you'll be solving for your unknown. Mr. Klintberg, makes a great reminder here about the use of signs. So anything in front of the mirror is real, and so the math actually works out here. It's just amazing how this math works. If you get a positive value, that means that that you're in front of the mirror. So if you get a positive DI, that means the image is in front of the mirror. If you get a negative DI, it means the image is behind the mirror. Something you do have to catch though, and it can trip you, is that's on the focal length. You saw here, I'll just back out so you can see it. Here, the focal length is behind the mirror. Okay, so this would be in a diverging mirror. The focal length is always negative, so you have to catch that, or else your math will get backwards. And then, of course, there is the reverse of that. If you come back up here to in this case, the focal length is in front of the mirror. So for converging lenses, mirrors. For converging mirrors, the focal length is positive. Okay, so that's important to note in this latter part here, and he kind of shows it again really nicely. Anything in front of the mirror is positive, behind the mirror is negative. And I guess on the right here, he does have a diverging mirror. He's flipped it. Okay, so you can read through these examples. I won't go through the math here because I think you guys can follow it easy enough. The last one I want to just mention is here is the magnification formula. Magnification. We had to use M here. Sorry about that. I mean, we use M for mass and meters and everything else, but in this formula, M stands for magnification. Okay. I call this the seven dwarf formula. It's the hi-ho dido formula. Off to work we go type thing. So but H is the height of the image, and HI is the height of the image. HO is the height of the object. And that's always above or below the principal axis. Okay, we try and keep that convention so we're not tripping on ourselves. And then DI and DO, you're familiar with those already. This negative is really important. You can't ignore that. So when you do the math, whatever DI is, stick it in. If DI is negative to begin with, then this negative that I just circled will make it positive. Okay. Outside of that, though, I don't think it's too bad. So coming up, we will be doing a little more practice. Again, you can look at that example, but that's an introduction to reflection.